Hello dear student, in the last lecture we have learned how to solve problems regarding the work done in producing a liquid surface. Let's continue our discussion. In the excess pressure on a curved surface, we know there is excess pressure on a curved surface. Maybe it concave or convex, it will have an excess pressure on either of one side. And this excess pressure can be calculated using a derivation. We have derived an equation for that, and the derivation from the derivation we will get the excess pressure P is equal to S into 1 by R1 plus or minus 1 by R2. It is usually 1 by R1 plus 1 by R2. If there is a case in which one surface is concave and another surface is convex, then we will change the sign as 1 by R1 minus 1 by R2, where R1 and R2 are the radius of curvatures of the two surfaces here. And if we have two surfaces, say in case of a thin film or a soap bubble, then the pressure will be 2 times of that of the pressure on the excess curved surface 1, that is 2 into S into 1 by R1 plus or minus 1 by R2. In some special cases, such as a spherical liquid drop or an air bubble inside a liquid, we know that for a spherical liquid drop or an air bubble inside a liquid has only one surface, and where R1 and R2 are equal to each other, and let it be R. Therefore, the equation will become S into 1 by R plus 1 by R, that is 2S by R. And also in case of a soap bubble, the soap bubble has two surfaces, therefore 2 times that of the pressure of a liquid drop, that is 4S by R. Similarly, in case of a cylindrical drop, we have only one surface, therefore it is S into and one of its radius of curvature. One surface is infinity, that is one side of a cylinder is a straight line, therefore its radius of curvature is infinity, therefore 1 by R2 goes to 0, and the answer is S by R. And in case of a cylindrical bubble, since we have two surfaces, it is 2S by R. Now let's move on and solve some problems. Problem number 1. The pressure inside a soap bubble is 1 millimeter of mercury, greater than the atmospheric pressure. What is the diameter of the bubble? Surface tension of a soap solution is given as 0.043 Newton per meter. So what is the question? In the question we are given a soap bubble. So we have a soap bubble, and we know the soap bubble has two surfaces, the surface number 1 and surface number 2. And also it is given that it has an excess pressure of 1 millimeter of mercury. It has a pressure greater than atmosphere inside here, that is 1 millimeter of mercury. So if this is the excess pressure inside this air bubble, we are asked to find the diameter of the bubble. So we have the equation, the excess pressure inside a bubble P is equal to, since it is a bubble, it has two surfaces and it has same radius, R1 and R2 are same, therefore it is 4S by R. Now this P is in Pascal, that is in the SI unit, and this here, the 1 millimeter of mercury is also a measure of pressure. So we need to convert it into SI unit. 1 millimeter of mercury, which is also a unit of measuring pressure, is converted as 133 Pascal. Therefore, from this equation, radius is equal to 4S divided by P and is given by 4 into S is given as 0.043 Newton per meter, that is in SI unit, and the pressure is 133 Pascal, and the answer is 1.29 into 10 to the power negative 2 meter. So what is this? This is the radius. We are asked to find the diameter. So let's multiply it by 2, and the diameter is 2 times 1.29 into 10 to the power negative 2 meter, which is 2.58 into 10 to the power negative 2 meter. So this will be the diameter of a air bubble which has an excess pressure of 1 millimeter of mercury. Next question. An air bubble situated just below the surface of water has a diameter of 1 centimeter. What is the pressure within the bubble if the atmospheric pressure on the surface is 10 to the power 5 Newton per meter, and the surface tension is 70 into 10 to the power negative 3 Newton per meter? So what are we asked to find? We are asked to find the pressure within the bubble. So we know that there is an increased pressure within the bubble, and we know there is an atmospheric pressure acting on the bubble. Right? There is a pressure inside the bubble P, and there is atmospheric pressure acting on the bubble, and there is no water column above this, so no water column is acting pressure on this. The air bubble is situated just on the surface, so the two pressure acting are just the atmospheric pressure and also the pressure of this water bubble, the excess pressure inside it. So this is an air bubble situated inside the water. So it has only one surface. It has only one surface. So we need to find the pressure inside the bubble. So atmospheric pressure P atmospheric is given as 10 to the power 5 Newton per meter. Other information given is the diameter as 1 centimeter. This implies the radius is 0.5 into 10 to the power negative 2 meter. We are given surface tension 70 into 10 to the power negative 3 Newton per meter. Therefore, the pressure, the total pressure will be the atmospheric pressure plus the pressure inside the bubble. And atmospheric pressure, we know it is 10 to the power 5 plus pressure inside the bubble. It has only one surface and it has a radius small r. Therefore, the answer is 2s by r. So, it is 10 to the power 5 plus twice of 70 into 10 to the power negative 3 divided by radius is 1.5 into 10 to the power negative 2, and the answer is this will come out as answer of this will be 28, and we will get an answer like 28 plus 10 to the power 5, approximately 10 to the power 5, but we can write it is 1.00028 into 10 to the power 5 Newton. So this is the pressure inside or the pressure experienced by the air bubble. Next question. Two soap bubbles of radii A and B coalesce to form a single bubble of radius r. If the external pressure P proves that the surface tension of the solution from which the bubbles are formed as S is equal to. Next question. Two soap bubbles of radii A and B coalesce to form a single bubble of radii R and of radius R. If the external pressure is P, prove that the surface tension of the solution from which the bubbles are formed is given by this equation, that is S into X is equal to P into R cube minus A cube minus B cube divided by 4 into A square plus B square minus R square, and assume that the temperature is constant. So what is the scenario? We had two bubbles, so two air bubbles, and these two air bubbles coalesce together, they combine together to form another bubble of radius R. So what is common in these situations? In this situation, it is given that temperature is a constant. So we have a law known as Boyle's law. This is from thermodynamics. That is, PV is a constant at a constant temperature. That is, pressure into volume is a constant. Therefore, pressure into volume of A, bubble A, PR, VR, pressure into volume of the final product will be equal to pressure into volume of the initial products. Therefore, we can substitute for that PR into VR, volume of the final product, that is 4 by 3 pi R cube is equal to PA into 4 by 3 pi A cube plus PB into 4 by 3 pi B cube. Therefore, on cancelling 4 by 3 and pi from every equation, we can write PR into R cube is equal to PA into A cube plus PB into B cube. But we know that PA, PR, PB are related to some external pressure. It has some external pressure P and it has some internal pressure. So, PR will be equal to external pressure P plus the internal pressure. Internal pressure is given by the equation 4S by R. Since it is soap bubble, it has two surfaces, so it is 4S by R. Similarly, PA is external pressure plus 4S by A, and PB is external pressure plus 4S by B. Substituting for this, we will get P plus 4S by R into R cube is equal to P plus 4S by A into A cube plus P plus 4S by B into B cube. On opening and rearranging, we will get P into R cube. From here it is minus A cube and minus B cube, and getting all the other terms to the next side, that is 4S into A cube plus B cube minus R cube. From this we can write an equation for S as S is equal to P into R cube minus A cube minus B cube divided by 4 into A square, since it is multiplied inside and we have here it is square terms, that is it is multiplied inside and we have an R term here, so it will cancel and this will become square. So A squared plus B squared minus R squared. Hence we have proved it. Next question. Calculate the depth of the water at which an air bubble of radius 4 into 10 to the power negative 4 meter may remain in equilibrium. The surface tension of the water is given as 70 into 10 to the power negative 3 Newton per meter. So, what are we asked to find? We are asked to find at the depth at which the air bubble will be in equilibrium. We know that an air bubble inside the water which has only one surface will have an excess pressure inside it, and this will be in equilibrium if the pressure acting on this liquid due to the column, due to the water column above it will be same as that of the excess pressure inside it. I repeat, the air bubble will be in equilibrium if the excess pressure inside it is equal to the pressure which is exerted by the water column above it. We know that pressure exerted by a water column of height h of density rho is given by h rho g. This is the pressure exerted by a water column, and the pressure, excess pressure inside the liquid, inside a air bubble in a liquid is given by 2s by r. So, these two pressures are equal, that is h rho g should be equal to 2s by r, so that the air bubble is in equilibrium. From this we can solve for h as 2s divided by rho g into r, and giving values 2 into 70 into 10 to the power negative 3. Since it is water, we know that rho is 1000, and the radius is given by 4 into 10 to the power negative 4, and g is 9.8. Therefore, height is equal to 3.57 into 10 to the power negative 3 meter. So, this height of the air column h have to be equal to 3.57 into 10 to the power negative 3 meter, around 0.3 centimeter. Next question. Two spherical soap bubbles A and B having a radius of 3 centimeter and 5 centimeter coalesce so as it produce a portion, a common surface. Calculate the radius of curvature of this common surface. So, we are asked to find a radius of curvature of this common surface which is produced by coalescing of these two bubbles. So, we are dealing with soap bubbles. So, we have two surfaces. Again, we know that in every equation for excess pressure, we have a 4s by r, 2s by r, etc. That is, the excess pressure P is inversely proportional to R. That is, as the radius increases, the pressure decreases. The smaller bubble has a greater excess pressure inside than a larger bubble. Therefore, the excess pressure inside a bubble of 3 centimeter will be higher than the excess pressure inside a bubble of 5 centimeter. So, this new surface formed will be curved like this. So, we need to find the radius of curvature of this bubble. So, excess pressure inside the first bubble, say excess pressure P inside A is given by 4s by R1, where R1 is 3 centimeter, and excess pressure inside B is given by 4s by R2, and this is before they have collided. So, after they have collided, what happens is that another pressure arises, and which is given by 4s by r, which will be the difference between these two pressure. Another pressure arises which will be the difference between these two pressures, that is 4s by r1 minus 4s by r2. And this excess pressure, that is another pressure arises, also can be written in the form of 4s by r, and we can solve for r from this, that is 1 by r is equal to 1 by r1 minus 1 by r2. Is 1 by r is equal to 1 by 3, it is in centimeter, into 10 to the power negative 2 minus 1 by 5 into 10 to the power negative 2. This will give you, say it is 5 minus 3 by 15, that is it is 2 by 15, and into 10 to the power negative 2. So, it is r, the value of r is equal to 7.5 into 10 to the power negative 2 meter, or which is 7.5 centimeter simply. So, the new surface formed will have a radius greater than both the bubbles. It is greater than 5 centimeter and 3 centimeter. It is 7.5 centimeter. Next question, derive an expression for the force required to separate two plates enclosing a thin liquid film. So, there are two plates, say two glass plates, they are enclosing a thin liquid film. If we have to pull one glass from over the other, we need to exert a lot of pressure. We have experienced this in our biology lab, that we need to separate two glass slides. After washing it, we need to exert a lot of pressure. So, we are asked to find how much force are we needed to exert on it. So, we know since there is a liquid layer inside it and it has only one surface, the excess pressure inside the liquid will be S into 1 by R1 plus 1 by R2, plus or minus 1 by R2. So, what is R1 and R2 in this case? This liquid has one surface over it. It will be of a circular shape of a radius r, and another surface is this thickness, that is the liquid which is enclosed in it will form a spherical shape, and it will have a diameter of d. Therefore, it again will have a radius of d by 2. So, these are the two spherical surfaces, and one is convex, that is it will be of this form, and another is concave, it is directed inside. So, we need to take one equation, that is we need to take a negative sign here. So, S into 1 by r, that is the radius of the higher, minus 1 by r2 here is d by 2. And in most of the cases, this r is very much greater than d by 2. So, we can exclude or eliminate this from the equation, and we can write excess pressure is equal to minus, we have a negative here, S divided by d by 2, or that is minus 2s by d. The sign negative indicates that we need to exert a pressure 2s by d per area, or the force 2s by d per area to separate these separate these plates. So, the force required to separate is given by pressure into area, and that is 2s into area divided by D, and this is the area of the plates. Therefore, we need to exert an excess force of 2S by D into area of the plates, so as to separate the plates. Also, you can see that the force is inversely proportional to D, that is distance between these plates. So, if the thin film is very thin, the force needed to separate is very high. If the thin film is not so thin, that is we have enough water inside those, the force required to separate will considerably reduce. The last question, two plain glass plates have a water drop pressed between them as a circle of a diameter 10 centimeter. The plates are 0.005 meter apart. What force perpendicular to the plates will be required to separate them? We are given with the surface tension. So, what are the quantities given? First of all, we have given that is the plates are 0.005 meter apart. That is, it forms a radius d by 2 which is given by half of this, and also we are given the radius r is equal to 5 into 10 to the power negative 2 meter. So, the radius of the area occupied by the water is this. So, we are asked to find the force. The water occupies a circular area of this radius. So, the force required from the equation is 2S into A divided by D, and we have 2 into S is given as 7 into 10 to the power negative 3 into what is the area? The area of a circular liquid drop which has a radius of 5 into 10 to the power negative 2. So, the area is pi r square. So, pi into 5 into 10 to the power negative 2 the whole square. So, this is the area divided by D. D is 0.005, and the answer here is 0.005 millimeter. So, the radius is 0.005 millimeter, which is again 0.005 into 10 to the power negative 3 meter, which is again 5 into 10 to the power negative 6 meter. So, this can be written as 5 into 10 to the power negative 6. On solving, we will get the force required to separate is 226 Newton. So, we need to apply a force of 226 Newton on the plates. Thank you for watching the video.